Hello, welcome everybody. So we are studying our fourth module of engineering mechanics. So a small introduction. We have already seen in our fourth module we have 4 parts to learn. That is, we studied about dynamics and types of motions. And comparing these both, we have 4 parts. Part 1, kinematics of rectilinear motion. Part 2, kinetics of rectilinear motion. Part 3, kinematics of curvilinear motion. And Part 4, kinetics of curvilinear motion. So among this, we have seen kinematics of rectilinear motion. And in kinematics of rectilinear motion, we saw how to apply the equation of motion for kinematics. That is how to determine the relationship between the distance, velocity and acceleration, the geometry of position of the bodies. That is what we saw in kinematics of rectilinear motion. Relation between the geometry, relation between the distance, velocity and acceleration. Then we saw, in kinematics there is the forces responsible for causing the motion is not considered. So second part is kinetics of rectilinear motion. In kinetics of rectilinear motion, we saw D'Alembert's principle. That is the extension of Newton's second law. And by applying D'Alembert's principle, how to solve the problems of kinematics. So F is equal to mass into acceleration. Summation of all the forces in the direction of motion will be equal to the mass into acceleration acting in the opposite direction. That is what we saw in kinematics of rectilinear motion. Now, we saw kinematics of rectilinear motion using Newton's second law or D'Alembert's principle. Now, looking into our syllabus, we have one more part, that is this part also, that is impulse momentum equation and work energy equation. So this also comes under kinetics of rectilinear motion. So kinetics of rectilinear motion can be solved by using D'Alembert's principle, by using work energy principle and by using impulse momentum equation. So by using D'Alembert's principle we saw the problems. And in our syllabus it is given impulse momentum equation and work energy equation, the concepts only. So we are not going into the problems, we will see only the concepts. What about the equation? Impulse moment. So two things we are going to see in this presentation. One is impulse momentum equation and the second one is work energy equation. And these two equations are also the extension of Newton's second law. So all the three equations, that is D'Alembert's principle, impulse momentum principle and work energy principle. All the three principles used to solve the kinetics of motion. Kinetics of motion of bodies are derived from Newton's second law, that is force is equal to mass into acceleration. So first of all we are seeing impulse momentum equation. I told you this is an extension of Newton's second law. So what is an impulse? Impulse is defined as a large amount of force acting at a short interval of time. So a very large force acting in a small duration, very small duration and large force. This is called impulse. It is nothing but force but acting in a short duration. So impulse is a force acting in a small duration. So it is nothing but I, impulse I is equal to sigma F into dt, force acting at a time period. So that is a small time period dt, sigma F is the large force. So the total impulse we are integrating is it from 0 to t. Now we know from Newton's second law F is equal to mass into acceleration. So summation of the force is equal to mass into acceleration. Now, acceleration, this A is equal to, we know dv by dt. Acceleration is equal to dv by dt. So from that we get sigma f into dt is equal to m into dv. So this equation, sigma f into dt is equal to m into dv, is called impulse momentum equation or impulse momentum principle. That is nothing but, see, we are integrating it from 0 to t, sigma f into dt is equal to mass into, we are integrating dv, change in velocity dv from u to v. So we get impulse is equal to mass into change in velocity, v minus u. Final velocity minus the initial velocity, that is nothing but change in momentum. Mass into change in velocity is called change in momentum. Mass into velocity is called momentum. mv is called momentum. Now mass into final velocity minus initial velocity, we will call it as change of momentum. So impulse is nothing but the change of momentum. Impulse is equal to mv minus mu. So impulse is equal to final momentum minus initial momentum. So change in momentum. So net force in the direction of motion multiplied by time, that is the impulse, is nothing but the change in momentum. Impulse is nothing but the change in momentum. So this is the principle of impulse momentum equation, an extension of Newton's second law used for solving the kinetics, problems on kinetics. Okay, when the net force acting on a body is 0, that is when F is equal to 0, our initial momentum will be equal to final momentum. So mv minus mu will be equal to 0. So mv is equal to mu, we get initial momentum equal to final momentum, and this is called law of conservation of momentum. Law of conservation of momentum. Initial momentum equal to final momentum when the net force acting on the body is equal to 0. I repeat, initial momentum equal to final momentum when the net force acting on the body is equal to 0, and this is called the law of conservation of momentum. Now we will move on to work energy equation. So in work energy equation we will study these things, these terms, that is work done, and in work done we will see what is the work done by a force, work done by a force of gravity, work done by a spring force, then about energy, that is kinetic energy and potential energy, and work energy principle and law of conservation of energy. So first one is work done by a force. So now we have a body of mass m. So we have a body of mass m, and this body we are applying a force F. We are applying a force F of angle theta, and we are moving this body from this position to this position. That is, we are moving this for a distance of s. Now, so consider a force F acting on a body with an angle theta with the direction of motion. So the displacement is taken as ds. Force is F, displacement is ds. How much distance it is moved? We know work done is equal to force into distance. So work done is equal to force in the direction of motion, that is F cos theta. This is moved in the x direction, in the horizontal direction, x direction. So when we resolve this force, we get F cos theta. Therefore work done is equal to work, that is the mass is moved from 0 to s. So integration of 0 to s, F cos theta into ds. That is the work done by a force. So force, summation of the force in the direction of motion multiplied by the displacement is the work done by the force. The next is work done by a force of gravity. So previous was work done by a force. Now work done by a force of gravity. So previous was the horizontal work done. Now this is the vertical work done. So vertical work done, it can be any direction, from bottom to top, or dropping from the height h, or throwing some object upwards. So now a body of mass m is displaced at a height h from its initial position. See, for this case we are assuming this is our initial position. This mass here, its initial position is at the ground level. So initial velocity is taken as u equal to 0, and from the ground it is displaced. This is moved to a height of h upwards. So the final velocity is taken as v. So mass is m, the weight of the object is mg. Now the displacement of the body is taken as dz, small displacement. You can take it as dh or dz. Now the work done by the force of gravity is the force into distance mode. Here force is nothing but our here force is mg, our weight is the force mg. So it is moved from a height from ground level to height h. So from integration is taken from 0 to h, and it is the displacement of the body is dz, small displacement is dz. We integrate, we get the work done, and this is given as minus indicates that the movement is upwards. So work done will be equal to mgh if the displacement is upwards. Minus mgh if the displacement is upwards, and mgh if the displacement is downwards. So this is nothing but the potential energy. Now work done by a spring force. So this is our original mass m. This is the spring. This is the symbol of spring. So using this spring, this mass is displaced in this position. So horizontally, when the spring is stretched, the mass is displaced. So the spring is subjected to a force Fs or F, and delta is the distance this mass has been displaced. It is delta, the distance displaced by the mass. So the parameter or the property of the spring is defined by a term called stiffness. Stiffness of the spring. Stiffness. You would have heard about stiffness and flexibility. Flexibility is the inverse of stiffness. Stiffness is the inverse of flexibility. So stiffness means how much force is required to produce unit displacement. In order to displace this object, what is the force required? That is the definition for stiffness. So the stiffness of spring constant K, that is this constant K is used to relate the force and displacement. So we call it as the spring constant. And this constant is nothing but stiffness of the spring. So the stiffness of spring constant K is defined as the force required for unit deflection. So force is equal to K into delta. F is the force applied, delta is the distance mode, and K is the stiffness. So force required to produce unit displacement is called the stiffness. Now the work done on the spring is force into displacement. So F into d delta. It is moved from x1 to x2. So integration of x1 to x2, F is k delta into d delta. So we get k integrate, we get it k delta square by 2. Half into k into delta square. So this is the work done by a spring force. So we saw work done by a force, work done by a force of gravity, work done by a spring force. So now energy. Energy can be kinetic energy or potential energy. So kinetic energy is the energy possessed by the particle by virtue of its motion. By virtue of its motion. So it is half mv square. Newton meter, and it is the Newton meter is nothing but joule. The unit of energy is joule. And potential energy is the energy possessed by the particle by virtue of its position. That is, potential energy is equal to mgh. That is work done by the force due to gravity. That is mgh. mgh, work done by the force due to gravity. That is potential energy by virtue of its position. Now, by virtue of its motion, kinetic energy is equal to half mv square. So, both the unit is joule. Now, work energy principle. So, again we are applying Newton's second law. We know force is equal to mass into acceleration. Now, force is equal to mass into dv by dt. Acceleration is equal to dv by dt. Now, this is dv by dt. We are multiplying one ds and dividing it by ds. So, we know ds by dt is v. Velocity is equal to ds by dt. So, we get m into dv by ds into velocity. ds by dt is velocity. So, we cross multiply, we get f into ds is equal to mv into dv. Now, we integrate this f into ds, that is, the object is moved from 0 to s. With the velocity, initial velocity is u and final velocity is v. So, here in the left hand side ds from 0 to s, right hand side the variable is the velocity, initial velocity to final velocity. So, f into integration of 0 to s ds is equal to m into integration of v to u v into dv. So, we get force into distance, Fs is equal to half m into half m v square, kinetic energy, half m into v square minus u square. We get v square minus, we integrate, we will get half m into v square minus u square. Integration of v into dv is v square by 2. So, we get 1 by v square by 2, we take 1 by 2 outside, we get v square. So, it is v square v square minus u square. So, work done, F into S is the work done, is equal to, this is nothing but kinetic energy. Half mv square is nothing but kinetic energy. So, final kinetic energy minus initial kinetic energy. So, work done is equal to change in kinetic energy. So, this is called work energy principle. So, today we saw what is impulse momentum equation or impulse momentum principle and work energy principle and work energy or work energy equation. So, with this our first two parts of the fourth module is completed. One more thing, law of conservation of energy. So, law of conservation of energy, energy can neither be created nor be destroyed. That is, one form of energy can be converted into the another form of energy, and this is called law of conservation of energy. So, energy, we all know that, you have already studied it. So, I think no more explanation is needed for you. So, with this, I told you in the first class, our fourth module is classified into four parts. So, first two parts is over by this. So, first part is the kinematics of rectilinear motion. We used equations of motions relating distance, velocity and acceleration. Part 2 is kinetics of rectilinear motion. So, three principles: D'Alembert's principle, work energy principle and impulse momentum principle. We have to solve the problems using D'Alembert principles, then work energy principle and impulse momentum principle, we have only the concepts. So with this, our half of the fourth module has been completed, and tomorrow, next class, we will be continuing our third part, that is kinematics of curvilinear motion, tomorrow. Okay, with this we will stop today. Hope you all understood. Thank you. And if you have any doubts, you can comment. Thank you. Thank you, everybody.